All right, next we want to talk about division. But to talk about division, we need to first introduce the notion of conjugate. So the conjugate of a complex number is fairly simple. You start with a complex number z, a plus bi, and the conjugate is just, you look at this point and you look at the reflection of that point, where the mirror is the real axis. So if you look at your real axis and you think about it as a mirror, so if z is looking at itself inside the mirror or into the mirror, it would look at this point, and this point here, we call it z bar, is the conjugate. And algebraically speaking, the only thing that changes between z and z bar is the sign of the imaginary part. So one thing to notice is that this point, the distance between z and the origin is the same as the distance between z bar and the origin, but if you look at the arguments, so suppose the angle here is phi for z, then the angle for the argument for z bar is going to be the same but negative. Like in this picture, it looks like maybe the argument would be 40 degrees for z, but it would be minus 40 degrees for z bar. So distances are the same, so the absolute value of z bar is the same as z, but the argument of z bar is minus the argument of z. And that's why the polar form of z bar is the absolute value of z times cos of minus phi I sine plus I sine of minus phi. So you need to change the sign of the argument. And of course the Cartesian form is the same. You just have to change the plus into a minus or the minus into a plus. Couple of quick examples. So algebraically, conjugate is a very straightforward operation. So if you want to compute 3 minus 4i, you just need to change the sign of the minus and it becomes a plus. So you get 3 plus 4i. If you want to compute the conjugate of minus 5 plus 7i, you need to change the plus into a minus. So you get minus 5 minus 7i. The conjugate of minus 2i, so you change the value of b into plus 2. So you get 2i, and then the conjugate of minus 5, so here the imaginary part is 0. So on real numbers, the conjugate does nothing. So the conjugate of minus 5 or minus 5 bar is just minus 5 again. So now on our road to do division, the next definition that we need is the notion of the inverse. So the idea here, it's a bit like matrices. There's one way to think about division as multiplying by the inverse. Just like, for example, if you are taking 2 and you're multiplying it by its inverse, you're going to get 1. So if you want to say 5, suppose you want to compute 5 divided by 2, you could be a creep and say that it's 5 multiplied by the inverse and get your 2.5. So we're going to see division as a multiplication by the inverse of the number you're trying to divide by. So what is the inverse, or where is the inverse in the complex plane? So I'll just explain it to you using my picture. So we are starting with a number z, a plus bi. And what we want to do is we want to find the inverse. So we know the inverse is going to be a number such that if you multiply z by its inverse, you're going to get 1. And we know multiplication, complex multiplication, means you multiply the distances and you add up the argument. And if you want to end up at 1, and we know that the polar form of 1 is, well, 1 is a number that is 1 unit away from the origin with an argument of 0. So we need to bring down z to 1s through multiplication. On my picture here, it looks like that my distance is somewhere around 2. So if I want to find a number that will be the inverse, I need to multiply 2 by something that will give me 1. So the inverse of 2 is 1. So here, what we can do is find that 1/2. So we want to start somewhere 1/2, and we want to find a complex number that is 1/2 units away from the origin. So the way you do this is, well, you create that circle. So we have that circle of radius 1/2, but now where on that circle is the inverse? Well, we need also to cancel out the the argument right now, it looks like my angle is like 40 degree. My God, circle's driving me crazy. So it looks like my circle is 40, my argument for z is 40 degrees, so you need to go in the other direction and cancel it. So on that circle, there's only one point that is 1/2 units away from the origin with an argument of minus phi. So here, the number that you're looking for, the complex number that you're looking for, the inverse of z inverse, is right here, 1/2 units away from the origin with an argument of minus phi. So that's why the absolute value of the inverse is 1 over the absolute value of z, and the argument of the inverse is the same as the argument of z, but multiplied by minus 1, which is strangely, what a coincidence, it's strangely the same as the argument of the conjugate. And we'll be using this in a moment. So you can see that the inverse and the conjugate are aligned in this with the same argument as z bar. And we're going to use this to actually construct a way to compute the inverse using the conjugate. And we're doing this with this remark here. The inverse can be computed as z bar over the absolute value of z squared. Looks like a kind of a weird formula, but it's very efficient algebraically to do some complex division. So if you look at the polar form of z inverse, so we know that the distance of the inverse is 1 over the distance of z, and the argument of z is minus phi. That's the polar form, but what we can do is if we multiply this z inverse polar form by 1, where 1 is just going to be the absolute value of z over absolute value of z, what will happen here is that you can see what I've marked in blue, this whole part, the absolute value of z times cos of minus phi plus I sine of minus phi, that's the polar form of z bar, and then at the denominator in red here, you just get the absolute value squared. So here we have a nice formula that computes the inverse of z simply by saying, okay, it's z bar, and z bar is not a difficult computation, and since we know how to compute absolute values, you take the conjugate, you divide by the norm square, and that gives you a nice formula for the inverse. And now you can use this to formally define division. So if you want to compute z divided by w, of course assuming that w is not 0, well, it's just z times z inverse. And of course z times w inverse, and because w inverse is w bar over the norm of w square, then you have an algebraic way to compute division. So again here, dividing by w is equivalent to multiplying by the inverse of w, or w to the power of minus 1. So let's just do an example. This example is basically the reverse example of our multiplication example. Let's divide 5 plus 5i by 2 plus i. We know the answer is going to be 3 plus i because we've multiplied before 2 plus i and 3 plus i, and we got 5 plus i. So of course if you take 5 plus i and you divide it by 2 plus i, you're expecting the 3 plus I. But anyways, let's do it. So the way I like to do this is, well, because I know the norm, so I'm dividing by 2 plus I, so the norm or the absolute value of 2 plus I, which is 4 plus 1, so it's root of 5, and the conjugate of 2 plus I, it's 2 minus I. So if I go 5 plus I divided by 2 plus I, the only thing I have to do is first multiply the numerator, the 5 plus I, by the conjugate of the denominator over the norm squared. So here the norm is root of 5 squared. So if you want some color here, so here's my root of 5 coming from here, okay, and my conjugate of 2 plus I is 2 minus I. So if you want some yellow, okay, and then you just FOIL normally. So 5 times 2 gives you 10. 5 times minus I, that's minus 5i. Then you distribute the 5i, you get 5i times 2, which is 10i. And the 5i times minus I, that's minus 5i squared. Of course, you remember that I squared needs to turn into minus 1. And now minus 1 times minus 5, that's plus 5 plus 10. That gives you your 15 here, and then the minus 5i plus 10i here was simplified to 5 plus I, and then 15 plus 5i divided by 5, you get back your 3 plus I. So just a small remark here, and I don't care how you do it, but you might see somewhere that some people do division this way. So if they have 5 plus 5i divided by 2 plus I, they simply multiply above and below by the conjugate, which is very similar to rationalization. And if you get to the exact same number at the end, which is fine, it's fine too. So I don't care how you do it, as long as you do it correctly. That's it. Bye-bye.